Thank you. So thank you so much for having me. I'm really happy to be here. My name is Silge, and I'm a data scientist at StackOverflow, and I am really thankful for being invited and for being here. And I'm here to talk to you about text mining, but approaching text mining from a particular perspective and using a particular idiom, and that is using tidy data principles and count-based methods to approach the kind of text mining tasks and natural language processing tasks that we often want to do. So the reason why this is something that I want to talk about and talk about why building tools like this and in developing approaches like this is important is that for people like me who work in industry, text data is increasingly important. This is almost like a silly thing to say, right? But like from industries from like healthcare to finance to like straight up tech, like where I work, and of course in academic, like most of you, where most of you work, like in basically any area, unstructured text data is proliferating, and there is great desire to use this to make decisions, to be able to understand how to use this. But data analysts and data scientists often come to this, this sea of unstructured text data that we're swimming in. We often come to this without formal computational linguistics training, without a background in natural language processing. Often, they're people like me, people who, I have a PhD in astrophysics. My training is in how to deal with numbers, how to deal with data that comes to me in like a table, like a rectangular form. So it is extremely important and valuable for us to understand how do we build tools so that people who deal with these, who are data scientists and data analysts can approach these texts. And the argument I want to make is that embracing these count-based methods that largely depend on how we count various things in the text that we're working on, and tidy data principles allows natural language processing tasks to be easier to reason about, easier to implement into tools workflows that are already in wide use, and more effective. So this is based. This talk that I'm going to be giving is largely based on an R package called Tidy Text that I'm one of the developers of, and also on a book here. So this book is called Tidy Text Mining with R, a Tidy Approach. So the book is available in its entirety at tidytextmining.com, and there are also paper copies of it that are around. So this is the kind of the basis of the approach that I want to talk about. So what do I mean when I talk about a tidy data structure for text? So let's look at a little example with Emily Dickinson. Let's look at a tiny little example here. So often text is stored in a computer as a string, right? Like in R, this would be how we would store it in what we might call a character vector or a string. We can store text as a corpus, where we would take a whole bunch of strings or documents and annotate them with some metadata. We can store textual information in a document term matrix, and these are all great data structures for storing text that have appropriate uses. I want to talk to you today about preaching the gospel of tidy data. So this is a way to store text information in a tidy form. What I mean by that is that there's one observation per row. The observation in this example that I'm showing you right now is a word, a single word. We could have other things that we're interested in as our observation. Our observation could be some kind of engram. Our observation could be maybe a sentence or even a whole chapter worth of text. But the thing that we're interested in here is a one observation per row, and then we have our data stored in a data frame in like a relational database type mental model of how we're storing our data. So notice a couple of things here when I have my data here in this tidy data structure. The other columns that I have other columns still around that are annotating each observation. So for example, I still know each what line from the poem each one of these words came from. I still know that. Also notice there are some defaults here that help me make some analysis later easier. So here is what the works of Jane Austen would look like in a tidy data structure. For every word, I know what book it came from. I know what line it's on. So in this case, line means like if I were reading the book in the format that I got it from, in this case from Project Gutenberg, I know what line of the file it was on, what chapter that word is from, and then I have all of Jane Austen's 6 published completed novels in this data frame. So that's what I mean by tidy text. So hooray, congratulations to us, we did it. Why am I interested? Why am I interested in doing this? The reason why this is an interesting approach of value is that there are many text mining tasks that become easy to reason about with commonly used tools once you embrace this approach. So for example, removing stock words, words that are uninteresting for analysis, like the, and, to, and of, becomes like an anti-join operation. Or sentiment analysis. Sentiment analysis can be implemented in multiple different ways, but one of the ways it's often implemented is with sentiment lexicons like these. And if you're going to take like a bag of words approach to sentiment analysis, then you can implement, if your data is in a tidy data structure, you can implement sentiment analysis using an inner join. So we choose one of our sentiment lexicons, and then we can implement sentiment analysis with an inner join. So we have our tidy data, we have our sentiment lexicon, we do an inner join between them. We have at the end of it the words that are in both of those data frames we had. After a few more lines of code that we have here, we can end up finding a net sentiment in each little like chunk of what I call it index here, like each little chunk of text, each little kind, and if we visualize the result of these just couple lines of code, we have a result like this. So we're able to see what is the net sentiment in each section of the novels of Jane Austen as we go through. Does this section have a lot of positive words? Does this section have a lot of negative words? And these sections with extended positive or negative sentiment align with events that we as human readers understand to be positive or negative events in the books. So for example, if you look at Pride and Prejudice there, and that middle section that has a lot of negative sentiment there in the middle, that is where Mr. Darcy proposes for the first time, and it's so terrible, and Elizabeth is so mad at him. And that section, 3/4 of the way through Pride and Prejudice, that has that extended section of negative sentiment, that is where Lydia elopes with Mr. Wickham, and it's a terrible scandal. So we're able to see narrative arcs through these novels using a count-based sentiment analysis approach that is very flexible and powerful. Perhaps more importantly, we're able to interrogate our sentiment analysis approach by seeing which words contribute to each sentiment. So we can say, okay, which words contribute the most to the negative and the positive sentiment? If we make some graph and inspect this here, first let's look at the positive words. These all look good, right? Which words contribute the most to positive sentiment in Jane Austen's novels? It's words like well, good, great, like, better, enough. This is all good, right? But now let's look at the negative side. What words are contributing the most to negative sentiment in Jane Austen's novels? We have words like poor, doubt, object, sorry, impossible. Those are all fine, but what about that top word, right? Miss in Jane Austen's novels is mostly used as a title for young unmarried women. So it should not be there. It should not be coded as a negative word. So we should go back to our sentiment lexicon and we should remove it from our sentiment lexicon and not count, we should count that as a neutral word, not as a negative word. So by using a count-based tidy data principle approach to sentiment analysis, nothing is a black box. It's in fact a clear, invisible box. We can interrogate our methods down and see exactly what's going on. So that makes it an important, powerful technique here. So the next thing I want to talk about is a programmatic way to talk about what is a document about and how we can use these kind of methods here. So term frequency gets at the question of how often is a word used in a document, and then inverse document frequency is a weight. So it's a weight that works like this. It's the natural log of the number of documents in a collection divided by the number of documents that contain some term. So let's say we have some collection of documents, and every document in that collection contains some word. Then that ratio is 1, and the natural log of 1 is 0. And that weight will go down. That will be very low. That will go away. So let's say we have our collection of documents, and some of the words only appear in one or very few of the documents. Then that ratio is a bigger number, and we take the natural log of that, and that's a higher number. That's a bigger number. So if we take term frequency and multiply it by inverse document frequency, we get what's called TF-IDF. And it's a statistic that measures something about words for documents in a collection of documents. And so what the idea of what it is supposed to measure is how important is a word for this document in the context of the collection of documents we're looking at. So let's look at an example. So first of all, we can look at term frequency very easily, just using plain dplyr style operation. So we get something like this. So in Jane Austen's novels, what are the total number of words and how often is each word used? So if we plot these distributions, they look like this, and these are very common distributions. They even have a special name called Zipf's law. And we have term frequency there. We have words that are used very frequently and words that are used not very frequently. And after that, we can go on and calculate a TF-IDF. So what are the words here? Let's look at the TF-IDF here of words like the, and, to, and of. You can see IDF is 0 because all of Jane Austen's novels contain the, and, a, to, and so TF-IDF is 0. But instead, if we take this data frame and we sort it, we arrange it so that we see the words that have the highest TF-IDF scores, we see different words. If you're familiar with Jane Austen's novels, you know who these people and places are, but even if you have no idea anything about Jane Austen, you know that these are proper nouns. So what have we found here? We have found that Jane Austen used consistent language from one novel to the next, and what is most distinctive about one of her works compared to the other are the people and places. The people and the places are the things that are most distinctive about each of her works. So TF-IDF is another one of these count-based methods that's extremely flexible and powerful. We don't only have to apply it to several hundred-year-old narrative text. In fact, we can apply it to technical documents just as easily. So for example, I worked on NASA metadata, so like description fields for NASA data sets at NASA. So if we look at what are the highest TF-IDF words and descriptions of NASA data sets, and then see how is that related, for example, to the keywords that are on the NASA data sets, we can see here that we again see very meaningful results that allow us to draw insight here. So if we look at, for example, the NASA data sets that are tagged with the keyword budget, the highest TF-IDF words there are words like fiscal, financial, OMB, and if we look at the data sets that are tagged with the keyword seismology, we see very different words. We see words that the highest TF-IDF words there are words like risk, earthquake, and so on. So TF-IDF is another count-based method that is flexible and powerful. So far, all of the examples that I've showed you have had the observational unit be a single word, but it absolutely does not have to be. We can extend that to be an engram, a sentence. So let's, for example, talk about just taking bigrams, just going up to sets of 2 words. If we look at our observational unit being 2 words, like a whole new world opens up where we can look at things like, for example, networks of words. How are words in a text associated together? What are the relationships between the words? We can start to get at questions of negation. How are negation words used, like not, never, don't? This can actually help you get at issues with, for example, sentiment analysis, like a bag of words sentiment analysis approach, like what I've talked about, has we'll look at a sentence like, I am not happy, and it sees that word happy, and it's not quite sure what to do. But if you use bigram analysis with negation words, you can get a handle on how often you're getting things wrong. You can also do an approach like this. You can do analysis like this, where you find all the bigrams that start with he and she, and then see which words are more likely to come after he compared to being more likely to come after she. So this is looking again at Jane Austen's novels. So in Jane Austen's novels, after she, you're more likely to see words like remember, read, feel, resolve. And after he, you're more likely to see words like stop, take, come, and reply. And we see here how women are central in Jane Austen, and we see it's about women's internal lives. It's about things that they're thinking and feeling, and men are external, like in Jane Austen's novels. It's things that they're doing. I worked on a project there we go. I worked on a project with the data visualization people at the Pudding for a very large data set of film scripts. So we took all the film scripts and we stripped out the dialogue, so that all that was left was the set direction. And then we found what words were more likely to come after he versus she in the set direction. And so after she, it was more likely to be words like she giggles, she squeals, she snuggles, and after he, was more likely like he gallops, he straps on a weapon, he kills. So we're able to see what are the stories that we're telling ourselves culturally about men and women, and so this comes from these count-based methods by being able to use bigrams here. What's my time?
13 minutes.
Oh, okay. Well, then I am going to talk about this. So I have been telling you how important tidy data is, how powerful tidy data is, but it is not necessary for your data to be in a tidy data structure at all stages of an analysis. We use the verbs tidy and cast, meaning tidy is to take your data to a tidy data structure, and cast is to take it to another data structure, like, say, a document term matrix. Having a workflow that involves tidy data structure can allow you to have a workflow, for example, that would say, okay, I'm going to clean my data, do exploratory data analysis. I'm going to understand what's on in my data, and then I'm going to cast to a document term matrix, and then I'm going to do some machine learning algorithm, say topic modeling, and then I'm going to take the output of my topic modeling, so whatever machine learning algorithm I want to do, and I can tidy it back to a data frame, and then I can use dplyr and ggplot to visualize the results of this. So this is a effective workflow that we have support for in the tidy text package. So we have tidiers and casters for the most well-used and common, for example, topic modeling packages that are used in R. So this is an example of topic modeling that I did on StackOverflow data. So I took StackOverflow questions and modeled the questions, and then after I did the topic modeling, so the topic modeling did not know about the tags. After the topic modeling, I said, what are the top tags associated with each topic? And we can see that there's a lot of meaningful collections of tags here. So topic 1 is a front-end web development topic. Topic 4 is a database topic. Topic 7 is the Python topic. So the topic modeling did not know about these tags ahead of time. The topic modeling was able to, using unsupervised machine learning, was able to infer that. So the last thing I want to talk about that I'm really excited about is about finding word vectors using count-based methods and tidy data principles. So probably most of you sitting in this room know about word vectors, but word vectors are ways to represent text using like numbers, using a vector. We can use them, you may have heard about them in the context of doing like word math, where you take some corpus and then you train the word vectors, and then you are able to do some word math like king minus man plus woman, and then what you get at the end is a word vector that is closest to queen. So you're able to say, oh, we're able to understand these semantic meanings of like king and queen by these word embeddings or word vectors. They are like word2vec and glove. These are typically trained using deep learning, using neural nets, but you actually can find them without deep learning at all, which is very exciting. So. You can find word vectors by taking a text, tokenizing the text, finding all the unigrams, calculating the probability that you find words together compared to how often you just see them in your text at all. So that is the pairwise PMI function there. So you're finding the pointwise mutual information, like how often you find things together. Here I have a window of 8, but that's something that you can change, like windows. That's something you actually have to decide with word embeddings as well too, actually. And then after that, you do a singular value decomposition. So you just do a straight matrix decomposition. And after that, what you do when you have let's take like the U matrix that you get out from a singular value decomposition, and that is word vectors. Like the rows of the U, or the columns, I think, of the U are word vectors. You just get out word vectors this way. So this method works shockingly well. So you may have seen this kind of approach in a recent blog post on the algorithms, on the Stitch Fix algorithms blog, and then I worked on implementing it in R here, which is very exciting. So I trained this on about 1 million posts from Hacker News. And so if you take the word vectors out here and you find the nearest synonyms to Python, it looks great. It's like Ruby, Java, PHP. The nearest synonyms to Bitcoin here are these things. The nearest synonyms to women are these. So we're getting really great results here, and we can also do the kinds of analogies, the kinds of word math that we talked about before. So OS 10 is to Apple, and then so OS 10 minus Apple plus Microsoft, and what we get is Windows. So when people are discussing OS 10 in the context of Apple, that is the same as discussing Windows in the context of Microsoft. So we're able to get the same kind of relationships, like what are people talking about on Hacker News, and these same kinds of contexts here. So, and because we did a singular value decomposition, we actually have principal components. So we can say, okay, so for this data set of like 1 million Hacker News posts, what are the components that contribute the most, that explain the most variation? So the first 2 are just general purpose English words. So do the posts contain a lot of those words or not? By the 3rd principal component, you start to have some technical words. Dimension 6 is about like energy and markets. Dimension 11 is about like geopolitics, and we can go down and we can see what are people talking about on Hacker News. So we've done like principal component analysis on a large text data set. We've gotten out tidy word vectors, and we can use the tidy word vectors to do regression. So this is another very fruitful. Powerful approach of these kinds of count-based methods here. So as I sum up, what I want to say is that count-based methods, like the ones that I've talked about, are accessible to people who come from backgrounds like me, who are working in industry, and for industry purposes, they are usually good enough. Like count-based methods and tools like this hold a lot of promise and a lot of ability for us to be able to solve real-world business problems. Does So thank you very much.